Good day, students. Today we will talk about the logarithmic functions. Before we start, do you know what are logarithmic functions? Logarithmic functions are the inverses of exponential functions, and any exponential function can be expressed in logarithmic form. Similarly, all logarithmic functions can be rewritten in exponential form. The exponential function y is equals to a to the power of x is equivalent to x is equals to the logarithm of y to the base a. How are logarithmic functions useful to us? Logarithms are really useful in permitting us to work with very large numbers while manipulating numbers of a much more manageable size. So let's try to express the following exponentials to their logarithmic forms. Number 1. 5 squared is equals to 25. In its logarithmic form is the logarithm of 25 to the base of 5. Number 2. 4 to the power of negative 3 is equals to 1 over 64. In its logarithmic form is negative 3 equals the logarithm of 1 over 64 to the base of 4. Number 3. 1 over 2 to the power of negative 4 is equals to 16. In its logarithmic form is negative 4 equals the logarithm of 16 to the base of 1 over 2. Number 4. 2 cubed is equals to 8. In its logarithmic form is 3 equals the logarithm of 8 to the base of 2. And number 5. 10 cubed is equals to 1000. In its logarithmic form is 3 equals the logarithm of 1000. Now let's try to express the following logarithms to its exponential form. Number 1. The logarithm of 36 to the base of 6 is equals to 2. In its exponential form is 6 squared is equals to 36. Number 2. The logarithm of m to the base of a is equals to p, and its exponential form is a to the power of p is equals to m. Number 3. The logarithm of y to the base of 3 is equals to negative 4. Its exponential form is 3 to the power of negative 4 is equals to y. Number 4. The logarithm of 15 is equals to x, and its exponential form is 10 to the power of x is equals to 15. And lastly, number 5. The logarithm of 1 over 8 to the base of 2 is equals to negative 3. And its exponential form is 2 to the power of negative 3 is equals to 1 over 8. Now let's talk about the properties of logarithms. Logarithm properties and rules are useful because they allow us to expand, condense, or solve logarithmic equations. The first property talks about the logarithm of 1 to any base is equals to 0. In symbols, that is, the logarithm of 1 to the base of a is equals to 0. Like for example, here in number 1, the logarithm of 1 to the base of 3 is equals to 0. The next property states that the logarithm of a to the base a is equals to 1. In symbols, that is, logarithm of a to the base a is equals to 1. Let's take number 3 as an example. The logarithm of 7 to the base 7 is equals to 1. Third property. The logarithm of a to the power of x to the base a is equals to x. In symbols, that is, the logarithm of a to the power of x to the base a is equals to x. Example, the logarithm of 5 squared to the base 5 is equals to 2. Next property, the logarithm of a to the base a to the power of x is equals to 1 over x. In symbols, that is, the logarithm of a to the base a to the power of x is equals to 1 over x. Example, the logarithm of 3 to the base 27 is equals to 1 over 9. So we need to find the exponent of the base, which is 27 is equals to 3 cubed. The next property is the logarithm of the product. Remember that the properties of exponents and logarithms are very similar. With exponents, to multiply two numbers with the same base, you add the exponents. With the logarithms, the logarithm of a product is the sum of the logarithms. Logarithm of mn to the base a is equals to the logarithm of m to the base a plus the logarithm of n to the base a. Next property, the logarithm of a quotient. This rule states that the ratio of two logarithms with the same base is equal to the difference of the logarithms. That is, the logarithm of m over n to the base a is equals to the logarithm of m to the base a minus the logarithm of n to the base a. The next property is the logarithm of a power. According to the power property of logarithm, the logarithm of a number m with exponent n is equal to the product of exponent with a logarithm of a number without exponent. That is, the logarithm of m to the power of n to the base a is equals to n times the logarithm of m to the base a. Example, the logarithm of 9 to the power of 4 to the base 3 is equals to 4 times the logarithm of 9 to the base 3. The last property talks about the logarithm of a root. The remaining exponent property is the power of a power. That is, the logarithm of n root of m to the base a is equals to the logarithm of m to the base a over n. Example, the logarithm of cube root of 64 to the base 5 is equals to the logarithm of 64 to the base 5 over 3. Now let's move on to the logarithms in expanded form. What does it mean to be in expanded? Expanded form, by definition, means the breaking up of a number according to their place value and expand it to show the value of each digit. When we talk about the logarithmic expansion, this is expressing a single logarithmic expansion into many individual parts or components. In this case, we must be able to apply the rules or properties of logarithms. Let us see in the first example. We have here the logarithm is equals to xy over z. Here, we are going to apply the property logarithm of a quotient, which means that the ones in the numerator will have a positive sign and the ones in the denominator will have a negative sign. So the logarithm x plus the logarithm y minus the logarithm z will be our final answer. Example number 2. The logarithm of 17x to the power of 5 to the base 6. To expand this logarithm, we need to use the product rule, the power rule, since there is no quotient here. Logarithm of a product can be used to simplify a logarithm of a product by rewriting it as a sum of individual logarithms. Using logarithm of a product, the logarithm of 17 to the base 6 plus the logarithm of x to the power of 5 to the base 6. The logarithm of a power means that the exponent will become the variable before the logarithm. Second, we will use the logarithm of a power. The logarithm of 17 to the base 6 plus the logarithm of x to the power of 5 to the base 6. We will arrive with the final answer, the logarithm of 17 to the base 6 plus 5 times the logarithm of x to the base 6. Another example, here we have the logarithm of 16x over y squared to the base 8. In this given, we are going to apply three properties: the logarithm of a quotient, product, as well as the logarithm of a power. First, with the logarithm of a quotient, we will have the logarithm of 16x to the base 8 plus the logarithm of y squared to the base 8. Second, with the logarithm of a product, we will have the logarithm of 16 to the base 8 plus the logarithm of x squared to the base 8 minus the logarithm of y squared to the base 8. Lastly, using the logarithm of a power, we will have 4 over 3 plus the logarithm of x to the base 8 minus 2 times the logarithm of y to the base 8. How did it become 4 over 3? We determined the logarithm of 16 to the base of 8. In order for us to determine the logarithm of 16 to the base of 8, we use the definition that both 8 and 16 are powers of 2. So we would equate the exponent. We have 8 to the power of n is equals to 16. That is equivalent to 2 to the power of 3n is equals to the 2 to the power of 4. Next, we would now cancel the base, which is 2. That would give us 3n is equals to 4. Then, cancel the coefficient n. That gives us to 4 over 3. So our final answer will be 4 over 3 plus the logarithmic of x to the base of 8 minus 2 times the logarithmic of y to the base of 8. Next example we have is the logarithmic of 4x to the cube over y to the base of 5. Here we can proceed with the rules in the order quotient, product, and then power. First, using the logarithm of a quotient, we have the logarithm of 4x cubed to the base of 5 minus 2 times the logarithm of y to the base 5. Next, with the logarithm of a product, we will have the logarithm of 4 to the base of 5 plus the logarithm of x cubed to the base of 5 minus the logarithm of y to the base 5. And lastly, using the logarithm of a power, we will have the logarithm of 4 to the base of 5 plus 3 times the logarithm of x to the base of 5 minus the logarithm of y to the base of 5. And that will be our final answer. Next example we have is the logarithm of x cubed y over 32 z to the power of 5 to the base of 16. Let's start with using the quotient rule. We have the logarithm of x squared y to the base of 16 minus the logarithm of 32z to the power of 5 to the base 16. Now we apply the product rule. The logarithm of x squared to the base 16 plus the logarithm of y to the base 16 minus the logarithm 32 to the base 16 plus the logarithm of z to the power of 5 to the base 16, followed by the power rule, 2 times the logarithm of x to the base 16 plus logarithm of y to the base 16 minus the logarithm of 32 to the base 16 plus 5 times the logarithm of z to the base 16. We define logarithm of x to the base 16 plus the logarithm of 32 to the base 16 as 16n is equals to 32, which is equivalent to 2 to the power of 4n is equals to 2 to the power of 5. And then we cancel the base, which is 2. We have 4n is equals to 5, and then we cancel the coefficient n, which gives us 5 over 4. So our final answer is 2 times the logarithm of x to the base 16 plus the logarithm of y to the base 16 minus 5 over 4 minus 5 times the logarithm of z to the base 16. From expanded, we will finally move to simplified. By the term simplified, it means simple. This is the reverse process of logarithms in expanded form, as logarithms in simplified form means combining or compressing the logarithmic expression into a single quantity. For example, the logarithm of 8 to the base of 7 plus 2 times the logarithm of x to the base 7 plus logarithm of 3y to the base 7. So we have all positive, meaning we won't be using the property logarithm of a quotient. So we will use the logarithm of a power and a product. We have the logarithm of 24x squared y to the base 7. Why 24? That is because 8 times 3 is equals to 24. Next example, the logarithm of y minus the logarithm of 20 plus the logarithm of 8x. There is the logarithm of 20, so that means we will be using the property logarithm of a quotient, and logarithm 20 will serve as our denominator. The logarithm 8xy over 20, and then our final answer will be the logarithm of 2xy over 5. How did it become 2 over 5? So we just simply divide or simplify 8 over 20, and that will give us 2 over 5. Next example, the logarithm of 9 plus 3 times the logarithm of 2 minus logarithm of 3. So there is a negative sign, so that means we will be using the property logarithm of a quotient, and logarithm 3 will serve as our denominator. Using logarithm of a power, we have logarithm 9 plus logarithm 2 cubed minus logarithm 3. And then next we use the logarithm of a quotient. We have the logarithm 9 times 2 cubed over 3. And then we simplify logarithm 72 over 3. And we have the logarithm 24 as our final answer. Next we have logarithm 9 minus 4 times logarithm 5 minus 4 times logarithm x plus 2 times logarithm 7 plus 2 times logarithm y. First, we use the logarithm of a power. Logarithm 9 minus logarithm 5 to the power of 4 minus logarithm x to the power of 4 plus logarithm 7 squared plus logarithm y squared. Next we have is the logarithm of a quotient. Logarithm 9 times 7 squared y squared over 5 to the power of 4 x to the power of 4. Next we'll multiply our simplified terms. Then we'll have the logarithm of 441 y squared over 625 x to the power of 4. And that is our final answer. Next we have 2 times logarithm of x to the base 6 plus 5 times the logarithm of y to the base 6. First we have is the logarithm of a power. Logarithm of x squared to the base 6 plus the logarithm of y to the power 5 to the base 6. And then we have the logarithm of a product, which is the logarithm of x squared y to the power 5 to the base 6. And that is our final answer. Next we will learn about evaluating logarithmic expressions. In evaluating logarithmic expressions, it would be easier if we put them in exponential form. In logarithmic expressions, we input results and get out exponents. Here are some examples. The logarithm of 1 over 49 to the base of 7. We will put the base of 7 in exponential form that will equate it to 1 over 49. In here, we can raise 7 to the power of 2, 7 squared, since this will be equal to 49. But since it is in a fraction form, so we will look back to the property logarithm of a quotient, which states that the 1 in the denominator is negative. Hence, logarithm of 1 over 49 to the base of 7 is equals to negative 2 as our final answer. Next example is the logarithm negative 8 to the base 1 over 2. In logarithmic expressions, there are some notes that we need to keep in mind. In this given, can we think of any number we can raise to 1 over 2 that will equal to negative 8? No, we can't. That is because a positive number raised to any number will never be negative, as you cannot take the logarithm of a negative number or 0. So our answer is undefined. Next we have the logarithm of 16 to the base 1 over 2. We put the base of 1 over 2 in exponential form that will be equal to positive 16. In this case, we can raise 2 to the power of 4, 2 to the power of 4 since this will be equal to 16. However, let's take a look at the given 1 over 2, which is a fraction, and remember the property logarithm of a quotient. Hence it will be 1 over 2 to the power of 4, and that will give us our final answer, which is negative 4. Next example is the logarithm of 1 over 8 to the base 64. So we put the base 64 in exponential form that will be equal to 1 over 8. In evaluating logarithmic expressions, analyzation is a must. Can we extract something from 64? Yes, we can extract the square root of 64, which will be equal to 8. In exponential form, that would be 1 over 2. Now since the given requires 1 over 8, we can have negative 1 over 2 to get 8 in the denominator. Therefore, the logarithm of 1 over 8 to the base 64 is equal to negative 1 over 2, which is our final answer. In the last example, the logarithm of 64 to the base 2. So we put the base 2 in exponential form, that will be equal to 64. We can raise 2 to the power of 6 as this will be equal to 64. Therefore, the logarithm of 64 to the base 2 is equal to 6, and that is our final answer. Now we will move on to solving the logarithmic equations. The difference between the exponential equation is that it is an equation in which the exponent contains a variable. A logarithmic equation, on the other hand, is an equation that involves the logarithm of an expression containing a variable. It contains logarithmic expression and constants. If one side of a logarithmic equation contains more than one logarithm, use the properties of logarithms to condense it into a single logarithm. Properties of logarithms basically change multiplication into addition, division into subtraction, exponent into multiplication, and radical into division. Here are some examples. The logarithm of 5x plus 7 to the base 2 is equals to 5. By the property logarithm of a power, let the given be in exponential form. That will be 2 raised to the power of 5 is equal to 5x plus 7. 2 to the power of 5 is equal to 5x plus 7. So we simplify 2 to the power of 5 is equal to 32. So we get 32 is equal to 5x plus 7. And then we transpose and combine like terms. 32 minus 7 is equal to 5x. Then it would result to 25 is equal to 5x. Divide both sides with 5 to get the value of x. 25 over 5 is equal to 5x over 5. Then we have our final answer, which is x is equals to 5. Next example is the logarithm of 2x plus 1 to the base 10 is equals to 3. By the property logarithm of a power, let the given be in exponential form. That will be 10 raised to the power of 3 is equals to 2x plus 1. Hence, 10 cubed is equals to 2x plus 1. So we simplify 10 to the power of 3 is equals to 1000. So we get 1000 is equals to 2x plus 1. And then we transpose and combine like terms. 1000 minus 1 is equals to 2x. Then we have 2x is equals to 999. And then we divide 2x over 2 is equals to 999 over 2. Our final answer will be 999 over 2 or 499.5. Next example, the logarithm of x plus 1 to the base 2 minus the logarithm of x minus 4 to the base 2 is equals to 3. We apply the property logarithm of a quotient to express the equation in a single logarithm. That will be the logarithm of x plus 1 over x minus 4 to the base 2 is equals to 3. Apply the property logarithm of a power to express it in exponential form. That will be 2 to the power of 3. Hence, 2 to the power of 3 is equals to x plus 1 over x minus 4. Then we simplify 2 cubed is equals to 8. Hence, 8 is equals to x plus 1 over x minus 4. To further simplify, cross multiply. So we get x plus 1 is equals to 8x minus 4. Then we apply the distributive property on 8 and x minus 4. So we get x plus 1 is equals to 8x minus 32. Then we transpose and combine like terms. 1 plus 32 is equals to 8x minus x. Then it would result to 33 is equals to 7x. Then we divide both sides with 7. 33 over 7 is equals to 7x over 7. So we have our final answer, which is 33 over 7 or 4.71. Next example, the logarithm of x to the base 4 plus the logarithm of x minus 12 to the base 4 is equals to 3. We apply the property logarithm of a product to express the equation in a single logarithm. That will be the logarithm of x to the base 4 minus x minus 12 equals 3. We simplify by applying distributive property. The logarithm of x squared to the base 4 is minus 12x is equals to 3. Apply the property logarithm of a power to express it in exponential form. That will be 4 to the power of 3 is equals to x squared minus 12x. We simplify 64 is equals to x squared minus 12x. We can solve for the value of x by factoring since it is a quadratic equation. X squared minus 12x minus 64 is equal to 0. That will be x plus 4 and x minus 16 is equal to 0. Get the values of x. X plus 4 is equal to 0. Transpose 4, x is equal to negative 4. Get the values of x. X minus 16 is equal to 0. Transpose 16 and it will become x is equal to 16. Final answer, x is equal to negative 4 and x is equal to 16. The last given, the logarithm of 2x minus 4 to the base 6 plus the logarithm of 4 to the base of 6 equals the logarithm of 40 to the base of 6. We apply the property logarithm of a product to simplify the logarithmic expression. That will be logarithm of 4 and 2x minus 4 to the base of 6 is equals to the logarithm of 40 to the base of 6. So first we have is to drop or cancel the logarithms. 2x minus 4 is equals to 40, and then we apply distributive property to simplify. 8x minus 16 is equals to 40, and then transpose and combine. 8x is equals to 40 plus 16. That will be 8x is equals to 56. And then we divide both sides by 8 to get the value of x. 8x over 8 is equal to 56 over 8. And then our final answer is x is equal to 7. How is learning about logarithmic function crucial in our everyday life? Math and life could never be separated as we make use of math in our everyday lives without even realizing it. Logarithmic functions can be applied in real-life scenarios such as earthquake intensity measurement, brightness of stars, and in chemistry such as the pH balance, a measure of acidity and alkalinity. The power of logarithmic function is that this is a very big help when it comes to exponential equations. With all that has been said, logarithmic functions are one of the most crucial concepts in our everyday lives. The Richter scale for earthquakes is a classic example of a logarithmic scale in real life. Decibels, light intensity, and pH balance are all well-known logarithmic scales. Logarithmic transformations are also extremely useful for making it easier to see patterns in data. When logarithmic transformation straightens out a function, it becomes the exponential function, making it much easier to read and more understandable, according to Burrell et al. 1999. Logarithmic derivatives are a lot cleaner for some complicated functions, as Fatos Marinas points out in his TDS article why logarithms are so important in machine learning. And before we end this lesson, here are some additional fun facts about logarithms. Didn't you know that logarithms were first used in India in the 2nd century BC? The first to use logarithms in modern times was the German mathematician Michael Stiefel around 1487 to 1567. In 1544, he wrote down the following equations. QMQN is equals to QM plus N and QMQN is equals to QM minus n. This is the basis for understanding logarithms. For Stiefel, m and n had to be whole numbers. John Napier, 1550 to 1617, did not want this restriction and wanted a range for the exponents. So, according to him, logarithms express ratios. A has the same ratio to B as C to D if the difference of the ratio matches. Mathematically, logarithm of A minus logarithm of B is equal to logarithm of C minus logarithm of D. Henry Briggs proposed to use 10 as a base for logarithms. Such logarithms are very useful in astronomy. Before electronic computers, logarithms were used every day by scientists. Logarithms help scientists and engineers in many fields such as astronomy. Before computers, the table of logarithms was an important tool. In 1617, Henry Briggs printed the first logarithm table. This was soon after Napier's basic invention. People used these tables to multiply and divide numbers. For example, a user looked up the logarithm in the table for each of two positive numbers. Adding the numbers from the table would give the logarithm of the product. The anti-logarithm feature of the table would then find the product based on its logarithm. So this is the end of our discussion. We've learned a lot about the logarithmic functions in this video. And if you're a little overwhelmed, don't worry. It might just take some time for it all to make sense. Remember, you can always re-watch this video a few times, and doing some of the practice problems will help it all sink in. Thanks for watching our video, and we'll see you next time.